So, good day students, and now it's time for the homework. Let's first look at what you shall achieve in this nugget. There are 3 overall aims. First, you shall be able to compute the amounts of combustion products from any fuel with a specific elemental composition. That is the dry substance or the dry ash-free substance analysis, different ash contents and different moisture contents. Second, you shall be able to compute the amounts of combustion products from any liquid or gaseous fuel with a given composition. And then you shall be able to adjust the amounts of combustion products with respect to excess air. When you plan an energy supply system based on biomass, there are 2 ends, and then of course there are the storage aspects in between. But first there is the question of what biomass is available in the region. That is one of the 2 starting points you must identify. And then there is the other end of the supply chain, and that is the end user you want to sell it to. These 2 endpoints determine which energy carriers can be used. You will see this clearly in the rest chains training material. So the energy carrier, which might very well be an upgraded fuel or something else, must be suitable to be produced from the biomass at hand, and it must be adapted to the needs of the final customer. And the final customer will use combustion to extract the energy from the fuel. So you, the planner, must identify and set the combustion properties of the fuel. Therefore, the first things you have to read are the sections in chapter 4 that covers the overall processes. After you've done that, then read the 3 appendices. The first one is mainly to repeat the basic structure of biomass from lesson 1 in this course. The second appendix on general fuel behavior is mainly to give you a short summary of some emissions aspects. The third appendix on ashes and ash behavior aims to clarify how the fuel composition and the combustion temperature may interact to generate operational problem for the end user. So when you read the third appendix, you shall bear in mind how the composition of the fuel may be altered by conversion processes. You learned about that in the second lesson. When you have studied these parts of the textbook, go back to column 4 and select the most relevant parts of the remaining 4 chapters. Now open the BusyPlan workbook and look at the second spreadsheet, the one called Biomass Properties. Roll down a little bit and you will see that there is a heating value calculator, and that further down there are links to databases for biomethane and biogas potentials. But there is actually nothing about the combustion properties. So what you shall do now is to produce a computer tool into which you can feed a fuel composition, the ultimate analysis of the dry, ash-free substance, allowing for a bit of inert ballast, the ash content, the moisture content, the lower heating value of the dry, ash-free substance, the oxygen content of the combustion air, and the percentage of excess air. Assume air to be dry and composed only of oxygen and nitrogen. The output shall be the amount of the main flue gas constituents, assuming complete combustion, the required amounts of combustion air, and the heating value of the fuel. You will use and further develop this tool in the coming nuggets and lessons, so you should put the appropriate work into it to make it flexible, and also to make it simple to expand so that you can include other aspects. I recommend you use rounded molar weights for the elements: 12 grams for carbon, 1 for hydrogen, 16 for oxygen, 32 for sulfur, and 14 for nitrogen. Skip the decimals. You can make this tool in Excel or any other spreadsheet program, or you can use professional programming tools like MATLAB or Scilab or whatever you feel like. Let us now have a fast look at the equations. First, the general stoichiometry for complete combustion. On this slide, I have allowed for 15 grams of other DAF constituents, though they were called inerts on the previous slide, and could amount up to 3% of DAF, the dry ash-free substance. From the fuel analysis appendix, you remember that ash analysis is always dry substance, while moisture content is always on a wet fuel basis. The air excess factor, lambda, is a proportionality constant taking a value of unity in case of the oxygen supply equaling the stoichiometric need. If the air supply is double, then lambda is set to 2, etc. In several industrial processes where high temperatures or extremely high combustion intensity or very high local heat fluxes are needed, it is common to use oxygen enrichment. Those working with CSS, carbon separation and storage, also use oxygen enrichment. Anyway, there is nothing to say that the combustion air must contain 21% oxygen. Use these equations to set up the calculation tool, and do not forget that the fuel moisture content will only be vaporized, so that the outgoing water content in the gas will be partly the incoming moisture and partly the water vapor formed by the combustion of hydrogen.